Okay, ladies and gentlemen, let's continue with lecture 13. We are still busy with chapter 4 in the textbook of Cengel and Ghajar. And chapter 4 is on transient heat conduction. It has 4 parts, and today we're going to do the last part. The first part was the lumped system approach. The second one was to look at transient heat conduction in large plane walls, long cylinders and spheres. The third group, or the third part of the chapter, was transient heat conduction in semi-infinite solids. And today we are going to look at paragraph 4.4, transient heat conduction in multidimensional systems. Okay. Now, in this approach of using multidimensional systems, we are going to use the previous work that we've done as, let's call it, as building blocks, except for the lumped system approach. So the 4 different geometries that we have considered, which are firstly the large plane wall, the large plane wall, and the large plane wall, that was the x-axis, and it had a thickness of 2L. Okay, so that was the first geometry that we've done, the large plane wall, and the second one was the long cylinder. With a radius R0, and that is its coordinate system R. So the long cylinder. Okay. The third one was the sphere. R also had a radius R0. So that is the sphere. And the fourth one was the semi-infinite solid. The semi-infinite solid had a plane wall, like that. That's the semi-infinite solid. And its coordinate system was an x-axis, the x-axis in that direction from the plane wall. So this is the semi-infinite solid. So with the multidimensional system approach, what we're going to do is we are going to use these 4 different types of geometries as building blocks. And it comes from the fact that in mathematics, you've done this principle of superposition, and specifically the product solution. Superposition and the product solution. But in the approach of using the principle of superposition, and if you go back into the mathematics, you will see it will be subject to 2 requirements. The first one is that all the surfaces should be exposed to the same T infinite and heat transfer coefficient. So all the surfaces that we consider should be exposed to the same environmental temperature and the same heat transfer coefficient. That is the first one. And the second one is that E gen should be equal to 0. So there should be no heat generation inside the body. So if we have those 2 requirements, then we can make use of the mathematical principle of superposition, specifically the product solution. And what we can do now is we can generate some other original geometries that we can also solve. Let's look at an example. Let's suppose we've got a plane wall, a large plane wall, which means it is infinite in this direction and in that direction. There it is like that. And we use the principle of superposition of a large plane wall and a cylinder. So what we can get now is in the intersection we can get this. Okay. And this large plane wall, let's suppose it has a thickness of A, and this radius is equal to R0. Then the result of this superposition will be what we call a short cylinder. And this short cylinder will have an height A and a radius or a diameter of 2 times R0. If you look at the textbook, figure 436, then you'll see a better sketch than mine. Okay, so it shows the intersection, shows the intersection of the plane wall and the cylinder. And then you should see the short cylinder as the intersection between the two. Okay, you see that? Okay, what does it mean? And how do we do it? Well, what is happening now is that we can say that the temperature, which is now a function of R, X, and T, okay, previously with all these geometries, the temperature was only a function of X and T. Of R and T, of R and T, and of X and T, not of 2 dimensions. Now we're going to have R and X. So the temperature is now going to be a function of 2 variables in terms of the Cartesian coordinates, the coordinate system being used. So the non-dimensionalized temperature, so it's the temperature minus T infinite, divided by the initial temperature minus T infinite of this short cylinder is equal to the temperature of xt, so it's only of x and time, minus T infinite divided by the initial temperature minus T infinite of a plane wall, multiplied by the temperature as a function of R and T. So it's only a function of radius and temperature, minus T infinite divided by T initial minus T infinite of an infinite cylinder. So the non-dimensionalized temperature of a short cylinder would be equal to the non-dimensionalized temperature of a plane wall multiplied by the non-dimensionalized temperature of an infinite cylinder. Thus, if we want to write it in a more shorthand notation, theta is our non-dimensionalized temperature, we can now say theta, which is now a function of r and x. Okay, r and x, and obviously t, time, because this is what this whole chapter is all about, getting the temperatures as a function of time, is equal to the non-dimensionalized temperature as a function of x and t of the plane wall multiplied by the non-dimensionalized temperature RT for the infinite cylinder. And when we consider this short cylinder, in terms of the limitations, that temperature on all sides should be T infinite, and the heat transfer coefficient on all the surfaces should be equal to H. So it must be the same. That was one of the limitations if we want to use this approach. Okay. So therefore, if this surface would be insulated, then we cannot use this approach. Okay. Do you agree? Okay, you should also disagree with me because there's a reason for that, and we'll come back to that later. But in principle, we want the same boundary conditions on all the surfaces. Okay. In terms of an infinite rectangular bar, if we are interested in an infinite rectangular bar, let's suppose we draw it like that, then that would be the solution of two plane walls. So the non-dimensionalized temperature as a function of x, y, and t for the rectangular bar, RB is the rectangular bar, is equal to the non-dimensionalized temperature for the plane wall in the x direction multiplied by the non-dimensionalized temperature of the plane wall in the y direction. Okay, so take note, in the x direction and in the y direction. And here we will have the x direction and the y direction. Okay. Now, if you look in Cengel, in table 4.5, Cengel and Ghajar, you will see 12 different geometries there, which were all generated by this principle of superposition. Okay. And if you are, for example, interested in the rectangular bar, if it's a very short one, then that is the solution. If it's a very long rectangular bar and you're not interested in what happens there at that surface and at that surface, then it would be equal to that one. So by using different solutions of superposition, you can actually generate all the temperature distributions, two-dimensional or three-dimensional, inside the bodies. Okay. What you have to be careful for is underneath it gives you the solution, so don't worry, you don't need to remember it firstly, and in the exam and test it will not be expected of you to think something like that all by yourself out. So you can get everything on the table. But what you have to be careful for is the coordinate system. If you look carefully at how it was generated, then you will see the x, y, z coordinate system are not always at the same place. It is not always at the center. And it comes out of the mathematics. Okay. So if, for example, you're interested in this type of body, okay, and you go and put your X, Y, and Z coordinate system there, then you're not going to generate the correct solutions. So you have to be very careful, put the coordinate system at the right place. Okay, let's look at an example. Okay, this example is a short cylinder, a brass one. Made from brass, and its initial temperature is 120 degrees Celsius. Okay. Its height is 120 millimeters, and its diameter 100 millimeters. The environment is at a temperature of 25 degrees Celsius, and that is all around the short cylinder. The heat transfer coefficient is equal to 60 watts per square meter degrees Celsius, or Kelvin, and we are asked to determine the temperature at the center. That is point 1 there. At the center at the top, and also there at that point there. Okay. So T1, T2, and T3, and that is after 15 minutes. We should determine those temperatures after 15 minutes. Okay, take note, T1 is in the center. It's on the center line, in the center of the cylinder. Okay, do you all have the problem? Short cylinder, height 120 millimeters, diameter 100 millimeters. It's made from brass. Initial temperature 120 degrees Celsius. T infinite 25. The outside temperature, T infinite 25, heat transfer coefficient 60. We want the temperatures T1, T2, and T3 after 15 minutes. T1 is at the center, and if we look at the table there at the top for the short cylinder, then you will see it is the third one. It is that one there. And take note where the coordinate system should be. Okay, where is it? It is in the center. Okay, so I'm going to take out this 120 because I need to put my coordinate system at that point there, R and X. You see, okay, and that is point 1 is there in the center. So if you look at that solution in the table, you will see that the short cylinder, all the mathematics behind generating the short cylinder is that it is the intersection of, firstly, a long cylinder with a radius R0 of 25 millimeters, 50 millimeters. With a radius of 50 millimeters, that is the first thing. And the second one is a plane wall of which has a thickness of 2L of 120 millimeters, which therefore mean L is equal to 60 millimeters. Okay. If you don't do this correctly, then the Biot number and everything is going to be wrong. So take a good look at the sketch, at the figure, and use the dimensions accordingly. Now let's start with the first part of the problem, T1. We want to get the temperature in the center. Okay. Now let's start with a plane wall. Okay. The plane wall. And if we think of this plane wall like this, and that is the x-coordinate system in that direction. To get to the center temperature, we need the temperature on this line. Do you agree? We need the temperature on that line there. Okay. So if that is equal to 120 millimeters, okay, then there are two approaches that we can follow. We can firstly use the Fourier series, where we use only the first term, or we can use the Heisler charts. I'm going to use the Heisler charts today. Okay, and the Heisler charts, if you look at them, then there are three of them, three charts. The first one gives us theta 0. What is theta 0? Theta 0 is firstly T0. T0 means it's on the center line. And it gives us the non-dimensionalized temperature on the center line as a function of the non-dimensionalized time divided by 1 divided by the Biot number. This one gives us the temperature at another place, but not on the center. But we need the center temperature first, and that one gives us the heat transfer. So this is the graph that we're going to follow. So we need to calculate the non-dimensionalized time, and we need to calculate 1 divided by the Biot number so that we can get theta 0. So let's start by calculating the non-dimensionalized time. It is equal to alpha t divided by L squared. Okay. Now what I forgot to write down is the K value for brass is 110 watts per meter Kelvin, and alpha is equal to 33.9 multiplied by 10 to the minus 6 square meter per second. Okay. So alpha is equal to 33.9 multiplied by 10 to the minus 6 multiplied by 15 minutes. 15 multiplied by 60 is 900 seconds. We want the solution of the 900 seconds. And L should be 60 millimeters square, and that is equal to 8.48. Okay. 8.48, the non-dimensionalized time, and 1 divided by the Biot number is equal to K divided by HL. K is equal to 110. The heat transfer coefficient is 60. The distance L is also equal to 60, and that gives us 1 divided by the Biot number equal to 30.6. If we look at the graph, Most probably it's going to be too small for you. Okay. But if we choose now the non-dimensionalized time equal to 8.48 up there, and 1 divided by the Biot number is equal to 30 is up there, then we can get the non-dimensionalized time. And from there, the non-dimensionalized time. Okay, take note of 0. X equals 0 is then equal to the temperature at the center, T0, minus T infinite divided by Ti minus T infinite. From the graph, it is equal to 0.8. And let's give it a number 1, because we're going to use that result later on again. Okay, so now we've got the temperature at the center. Let's look at the cylinder. For the cylinder, there's the cylinder, and that is R, and for the cylinder we need the temperature on that line. Okay. Because the temperature at point 1 is going to be the intersection of that solution and that solution to give us point number 1. Okay. So the non-dimensionalized time is equal to alpha t divided by R0 square. Where do I get it? From the Heisler charts. Don't need to remember it. If you just look at the Heisler chart, there at the bottom you can see this non-dimensionalized temperature is equal to that, alpha t divided by R0 square. Alpha is equal to 33.9 multiplied by 10 to the minus 6. The the time is 900 seconds. R is 50 millimeters, so it is 0.050 square, and the result is the non-dimensionalized time of 12.2. 12.2. Then 1 divided by the Biot number, we also need is equal to K divided by HR0. K is the thermal conductivity of the brass, which is 110, divided by the heat transfer coefficient, which is equal to 60, multiplied by the radius, which is 50 millimeters, 0.050, and that is equal to 36.7. Okay. From those two values on the Heisler chart, we can get the non-dimensionalized temperature for a cylinder, where R is equal to 0, which is equal to the temperature where R is equal to 0, T minus T infinite divided by the initial temperature minus T infinite, and that is equal to 0.5 according to the graph, and let's call that number 2. So firstly, for the plane wall, we've calculated the non-dimensionalized temperature on that line. Then we do it for the cylinder, calculate it on that line, and now we put it together by saying that the temperature now, as a function of x, r, and t, is equal to the temperature where it's the temperature where X is equal to 0, where R is equal to 0 also, T minus T infinite divided by Ti minus T infinite is also equal to the non-dimensionalized temperature of the wall, where X is equal to 0, T multiplied by non-dimensionalized temperature of the cylinder, where R is equal to 0, and that is equal to 0.8 multiplied by 0.5, which is equal to 0.4. 0.5 multiplied by 0.8 multiplied by 0.5, which is equal to 0.4. Okay. But the non-dimensionalized temperature is not really what we are interested in. We want to know the temperature in degrees Celsius. So we can say the temperature where X is 0, where R is equal 0, T minus, or rather, sorry, ladies and gentlemen, let's rather put it as point T1. T1 minus the environment temperature is 25, the initial temperature is 120, the environment temperature is 25, and that is equal to 0.4, and that gives us the temperature at point 1 as equal to 63 degrees Celsius. 63 degrees Celsius, so it is the intersection of the plane wall at its center line multiplied by the cylinder on its center line to give us the temperature at point 1. Any questions before we move to point 2? Okay. Now, in many cases, this is now where students experience it as starting to become a little bit difficult. But it's really not difficult. Just stay calm. Let's look at point 2. So we want to calculate the temperature now, T2. Okay. Now, to get T2, we need to look at the plane wall on the outside surface. We need the solution of a plane wall on the outside surface. So if this is our plane wall, like that, X there, we need to get the temperature on that surface there. Okay, now if we want to get temperatures which are not at the center, in terms of the Heisler charts, that first chart is when you want to get the center temperature. This is the chart when you want to get the temperature which is not at the center. Okay, so you can see from the chart what is required. So what we need is X divided by L. We need to get the solution at X divided by L. Okay. What is X going to be on the surface? X on the surface is going to be 60 millimeters, 0.060. L is also 60 because that is equal to 2L, which is 120. So that is also equal to 60. So we need it at X divided by L equal to 1. Again, we have to calculate 1 divided by the Biot number. It's equal to K divided by HL. And you will see we've already calculated it. Okay. We've already calculated it. It is equal to 30.6. So that didn't change. Okay. So with those two, we can go and get theta divided by theta 0. Okay. Theta 0 means on the center. And that is from the graph equal to 0.98. And that means it is the temperature at L, where x is equal to L, T minus T infinite, divided by T0 minus T infinite. And there's more than one way how you can solve it now. You can say, well, the non-dimensionalized temperature is equal to 0.98 multiplied by theta 0 is equal to 0.98 multiplied by 0.8 from our previous solution at 1. So this is the non-dimensionalized temperature at the center, which is equal to 0.8. So now we take the 0.8, multiply it by the 0.98, and that gives us 0.784. So therefore we can say that the temperature at L, T minus T infinite, divided by Ti minus T infinite is equal to 0.784. So that is the non-dimensionalized solution on the surface. Let's look at the cylinder part. The cylinder, if we want to get the temperature exactly there in the center, we need the solution on the center line. Okay. So if this is our cylinder, we need to get the solution for this one on that line, which we've already done. We've already done that. Okay. So we can just say our previous solution from our previous work from 2, we can say that the non-dimensionalized solution for a cylinder at 0T is equal to 0.5. Therefore, now that we've got the solution on the plane, on the surface and in the center, we just need to multiply them. We can say that the temperature at L0T minus T infinite divided by Ti minus T infinite is equal to the non-dimensionalized temperature of the plane wall at LT multiplied by that of the cylinder at 0T. Which is equal to 0.784 multiplied by 0.5, which gives us 0.392. And let's also keep that one as solution 3, because we're also going to use that later on. Okay, now this temperature at L, which is on the surface and on the center line, is equal to T2. T2 minus T infinite is 25. The initial temperature is 120 minus 25, from which we can solve that the temperature at point 2 is equal to 62.2 degrees Celsius. Okay, any questions, ladies and gentlemen? Okay. Now we have to move to point 3. Okay. Now we have to move to point 3, so it's that point there. Okay. To get the temperature at point 3, the non-dimensionalized temperature, XRT, is equal to the non-dimensionalized temperature for the cylinder, at RT multiplied by the non-dimensionalized temperature for the wall. That is the general solution. Where do we want to calculate it now? Well, that would be at the cylinder where R is equal to 50 millimeters. Okay. R is equal to 50 millimeters to get point 3 for us. Multiplied by the solution of a wall, multiplied by X, and X must be equal to, from there to get to there, X must be equal to 50 millimeters, 60 millimeters, sorry. So that is equal to 60 mils. Okay. So that's the principle. The principle. Let's first look at the cylinder. That would be the solution of the cylinder on the outside, where R is equal to 50 millimeters. So if we make a drawing here of our cylinder, it is on the outside, where R is equal to 50 millimeters. Okay, do we have that solution already? Do we have that solution already? Okay, so if we look at the solution of a cylinder, let me get that Heisler charts again for you. We first need theta divided by theta 0 as a function of 1 divided by the Biot number as a function of the non-dimensionalized time. So the non-dimensionalized time we've already calculated, that we've calculated, and we've got that value already, theta 0. You agree? Okay. Then we go to the next graph, which gives us, that one is theta 0. Theta 0, this one is theta divided by theta 0. As a function of R divided by R0. What must R be equal to now? R divided by R0 is going to be equal to 1. Okay? So from that we can calculate theta of the cylinder at 50 millimeters as a function of time. You agree? Okay. Then we need the solution for the plane wall on that surface there. Okay. So the solution for the plane wall at 0.06 at 60 millimeters is a function of time. We've got that solution. Plane wall on the outside, here it is. Do you see? This non-dimensionalized temperature here, theta is equal to 0.784. Okay. Who of you can quickly go and calculate that value for me? Theta. I'm going to give you a minute or two. Try to calculate that value for me.
So we need
which must I first enlarge that one? Able to see it? That one or the other one? Okay. Can you calculate it quickly for me? Okay, you can go and check it, but I think it is equal to 0.475. 0.475. Let's just finish the problem. Okay. And that then gives us the solution, which is equal to 0.475 multiplied by 0.784. Which is equal to 0.186. Okay. Therefore, the temperature at point 3 minus T infinite divided by Ti minus T infinite is equal to 0.186. From where we can solve that the temperature at point 3 is equal to 42.7 degrees Celsius. Okay, any questions?
I got double reset of 2.
For which one?
The last sigma value that you
this value? This one? Okay. Okay. You just check the calculations. Ladies and gentlemen, wait a minute. We are not finished. We're not finished. Okay. Just go and check the last calculations here. Maybe there's an error here. It seems as if there is. But a very important thing now is, let's suppose, and I've asked you that at the beginning, let's suppose I give you a problem where this cylinder is standing on an insulation material. And the cylinder, the height of the cylinder is 20 millimeters, and the diameter is 30 millimeters. How are you going to solve that problem? If you look in your textbook now in terms of the possible solutions, which one will you use? Which solution will you use? you can see a plan to be made? Who would like to use the short cylinder? Okay. Nobody? Why not? Okay. The reason why we cannot do it is that, remember, the limitation is that T infinite must be the same on all the boundaries, which obviously it is not. It is not equal to T infinite on that boundary. However, remember that there's something like symmetry in nature. Okay. So we know that there will be the temperature gradients there would be equal to 0. So if I take this same cylinder and I say, well, let's consider a cylinder, I double the length and I make it 40 mils, and now I put the coordinate system there, I can solve the same problem. You agree? Okay, so be careful for things like that. Just use symmetry in nature, and you can solve many more problems than shown in table 4.5. Thank you, ladies and gentlemen.